Over the last 500 million years, the fossil record reveals 5 major mass extinctions. In each case, some kind of global catastrophe wiped out a significant fraction of species, evidenced by these dips in the number of marine animal genera. The most recent of these famously knocked off the dinosaurs and was likely triggered by an asteroid that impacted Earth and formed Chicxulub crater, death from above. But over the last 20 years, scientists have proposed a different kind of astronomical threat that could also explain the late Ordovician extinction event, a type of event that is so powerful it could make entire parts of the galaxy inhospitable to life. So stick around to the end of the video to find out what. The idea of astronomical threats raises the question, could there be safe and unsafe parts of the galaxy? Enter the so-called galactic habitable zone. Now, you've probably heard the phrase habitable zone before, but in a rather different context, as it's usually thrown around when talking about the region around a star where rocky planets could have liquid water. Although one can get pretty deep into the nuances of how to define this zone, it's actually pretty simple. It all comes down to thermal energy. In fact, it's so simple that even a child, such as Jackson Kipping, can explain it to you.
When the planet is too close to the star, it gets fried. When the planet is too far away from the star, it gets frozen.
So the habitable zone of a star is easy enough to understand. But some astronomers have taken this idea a step further and have proposed that there exists a galactic habitable zone, an idea which is more nuanced and indeed more controversial than its circumstellar brethren. As alluded to at the top of this video, many discussions of this zone tend to focus around catastrophic extinction level threats to life. That's unlike the circumstellar habitable zone, which is really just telling us where is it warm enough for liquid water. And such concerns are not unreasonable because at the end of the day, the galaxy is a largely hostile place to life. Space is under no obligation to be hospitable to thinly clothed primates or even much hardier life.
If you can't take a little bloody nose, maybe you ought to go back home and crawl under your bed. It's not safe out here.
The idea of a galactic habitable zone has been kicking around since the 1980s, with supernovae often held up as a primary threat to life. Different parts of the galaxy have different supernovae rates, and being too close to such an event is undeniably a potential threat to life. But ever since its inception, the idea of a galactic habitable zone has always been a controversial hypothesis. So why is this? First, critics often accuse proponents of essentially making too much of our location in the galaxy. At the end of the day, we have to live somewhere in the galaxy, but that doesn't mean that it is a special somewhere just because we live here. In other words, stop staring into the tea leaves so much and just move on. Second, the galactic habitable zone rests upon a set of more speculative arguments than the circumstellar version. In the latter case, it's in principle a precisely calculable range of distances, the well-understood range where liquid water is stable, although in practice there's a lot more nuance involved there. In contrast though, the galactic version sits upon shakier claims. For example, it argues that the supernova rate can't be too high, else you'd get too many mass extinction events from which life couldn't recover. But the problem is, no one really knows how much is too much. After all, even if the late Ordovician extinction event were indeed caused by a cosmic threat, that only establishes that we're here in spite of such events. In fact, some have even argued that some low rate of mass extinctions is a good thing, allowing evolution to take an occasional reset and try something new. So you can see that the galactic habitable zone is a slippery concept, one resistant to firm quantification, even if we had a complete understanding of supernova rates and other cosmic threats. And that has made it unpalatable to many scientists. In fact, I even heard some colleagues call it pseudoscience. But really, all of these critiques are just statements about our current ignorance. The fact that we don't presently understand the range of mass extinction level events necessary for intelligence evolution doesn't mean that the basic idea is wrong, although it might be. More importantly, it is a fully testable hypothesis, and so on that basis, I think that it is fair to call it a legitimate and credible scientific theory, just one that hasn't been verified or falsified yet. So let's move on from that concern, but remain cognizant of the uncertainties involved, and instead, let's now dive a bit deeper into some of the arguments underpinning this idea. So far, we've discussed supernovae as a possible threat to life, hugely powerful stellar explosions that can outshine entire galaxies. Your risk factor from a nearby supernova primarily depends upon how packed your neighborhood is. If you live within an area jam-packed full of stars, then naturally the risk that one of those is massive enough to go supernova sometime soon is going to go up. It's like how there are more crimes per square mile committed in cities rather than rural areas. Now, since the center of the galaxy is as busy as it gets, I mean, it's like the Times Square of the galaxy, this immediately tells us that we might question the habitability of the galactic core then. But to be honest, you really have to be pretty up close and personal to a supernova for it to pose any kind of meaningful threat to life. That's why astronomers were not freaking out at the prospect of Betelgeuse going nova when it started acting weird a few years back, something we talked about on this channel. Probably the longest range impact a supernova could have on Earth is stripping our ozone layer by bombarding the atmosphere with high energy radiation, especially gamma rays. So this is a far cry from the dramatic scenes you might naively imagine when you think of a nearby supernova going off, perhaps obliterating a planet or something like that. But nevertheless, this still poses an existential threat to us. Atmospheric modeling by Thomas et al. Finds that if the gamma ray energy per unit area that strikes the atmosphere, also known as the fluence, exceeds 100 kilojoules per meter squared, then it would deplete 91% of the ozone layer in a local region and 36% globally. Just to give some context, the energy here is equivalent to detonating about 500,000 Hiroshima atomic bombs above the Earth's atmosphere. So yes, this is a pretty bad day for Earth. Now what's really happening is that the gamma rays are sufficiently energetic that they can unbind the ozone molecules, which is 3 oxygen atoms stuck together. Ozone protects us from the sun's ultraviolet radiation, and so without it, surface life will suffer significant DNA damage. Even a 50% reduction in ozone would triple our exposure to damaging UVB light, and no, this won't give us all superpowers, I'm afraid. But things are actually even worse than this, because the dissociated ozone then goes on to react with dissociated nitrogen and form nitrous oxide and dioxide, which act as catalysts for depletion of ozone. Moreover, the nitrous dioxide is opaque and reduces the amount of sunlight that reaches the surface, leading to a global cooling event, an event which is also thought to occur during a nuclear winter. Put together then, life in the deep oceans might be okay, but life on or near the surface will suffer. So that's the bad news, but the good news is that in order for a supernova to cause this level of damage, 100 kilojoules per meter squared, you have to be pretty close to it. Unfortunately, there is some disagreement in the literature about exactly how close we're talking about here, and of course this will also depend upon what kind of supernova we're thinking of. Spinelli et al. Estimate for the most energetic Type 1a events, it would have to be within 6 light years of us to reach a fluence of 100 kilojoules per meter squared, and that becomes a measly 2/3 of a light year for Type 2 supernovae. In contrast, Gorels et al. 2002 come up with 8 light years for the Type 2 supernovae, after scaling their numbers to the same critical fluence. So, whilst frustratingly there is an order of magnitude disagreement in the literature here, both of them do agree that supernovae have to be very close on a galactic scale to pose a serious threat. So, all of this implies that supernovae just really aren't that threatening after all, at least in this part of the galaxy. But what if we move to the inner core of the Milky Way? Surely there, the density of stars is much higher, and so we should expect supernovae to become a significant threat, right? Well, not really. Spinelli et al. Estimate that even in the inner sanctums of the Milky Way, the expected rate of mass extinctions induced by supernova is a handful per 500 million years. That's a number sufficiently low that we could be confident that even life on Earth here should be able to recover and thrive again. So when it comes to supernovae, basically the entire galaxy is currently habitable. Supernovae are not totally irrelevant though, because the current state of our Milky Way galaxy is not the way that it always was. In the past, there was more gas enabling higher rates of star formation. More star formation means more massive stars, which in turn means more supernovae. And indeed, if we look back in time, the inner core of the galaxy looks to be a far less hospitable place than it is today, shown here by these red regions. So, if you found yourself living close to the galactic core, so that's positions towards the left-hand side here, and living early on in galactic history, that's positions near the bottom of the diagram, then yes, you would be in trouble. But more or less everywhere and every when else, I think you'd be okay. Now, if supernovae were the only cosmic threat out there, then I might agree with those of you who think that the galactic habitable zone should be disbanded. But actually, there is a far more dangerous threat out there, an event that is in fact 1,000,000 times more powerful. Indeed, it is this event that is hypothesized to explain the late Ordovician mass extinction event. So, what is this threat? Gamma ray bursts. So, what are these? Gamma ray bursts were a complete mystery when they were first observed in the late 1960s by the US military's Vela satellites, which were designed to monitor nuclear weapon detonations. We've now detected many thousands of such events though, and our understanding has certainly improved but remains an active area of development. Two broad categories of gamma ray bursts appear to exist. There are short gamma ray bursts which last for less than a couple of seconds, and there is a far more dangerous longer gamma ray burst that persists for many seconds or even many minutes. The short flavor appears to be associated with merging neutron stars, since when LIGO observed such an event on August 17, 2017, both the Fermi and Integral Gamma Ray telescopes detected a short gamma ray burst alongside it. In contrast, the longer bursts appear to be associated with Type II supernovae, which are less confusingly called core collapse supernovae, basically massive stars that collapse in on themselves when they die, forming black holes or neutron stars in the process. And it's during this process that two narrow beams of high energy radiation are ejected from the poles of the star, typically just a few degrees in width, and that's the gamma ray burst. Now, not all supernovae do this, and even amongst those that do, you won't necessarily see a gamma ray burst because you have to be aligned along those thin pencil beams coming at the north and south pole. But if you are, boy do these things shine, briefly producing 100 trillion times more energy than our sun, or equivalently 10,000 times more energetic than our entire Milky Way galaxy. Suffice to say that gamma ray bursts are not to be trifled with. Fortunately, gamma ray bursts are about 10,000 times rarer than supernovae, but what they lack in frequency, they more than make up for in power. So much so that they pose a far greater threat to us than supernovae do. Now, it's worth noting that the actual threat mechanism here is broadly similar to that of supernovae, stripping away our ozone layer. But whereas a supernova needs to be within a few light years or so in order to pose a significant threat, a gamma ray burst can do the same level of damage from a staggering distance of 6,500 light years. Recall from before how we showed this space-time map of extinction level event frequency coming from supernovae. The red regions here are too dangerous, whereas green is safe. For supernovae, only regions close to the galactic core and early on in galactic history were hazardous. Now let's see the same map for gamma ray bursts. It's a far more frightening picture, with huge swaths of the Milky Way space-time diagram becoming dangerous. Interestingly, the galactic core starts out very hazardous, but actually seems to peter out. There's still plenty of stars there, so what's going on? The answer is thought to be metallicity. There's a growing body of evidence that the rate of gamma ray bursts is anti-correlated to the metallicity of that region, by which, to clarify, astronomers really just mean elements heavier than helium. So fewer metals means more gamma ray bursts, although the exact reason why remains unclear. One idea is that high metallicity stars shed their mass more easily, leading to a slower rotating core at the moment of collapse. That in turn means that there's less angular energy available to trigger the gamma ray bursts. But frankly, we don't know for sure, and this is largely an observational trend rather than something that we deeply understand. One thing we are more confident about is that the galactic core shown here should start out with few metals, just like the rest of the galaxy. But because there's so many stars there, it has more supernovae and thus more metal-enriching events, which consequently dial down the gamma ray burst rate. On the outskirts of the galaxy, over here, there's also few metals, but there's also few stars period, so not much chance of a gamma ray burst. So that explains why this map has green regions in the core and galactic outskirts. What this means is that we end up with a sweet spot in between those two at intermediate radii, but really a deadly sweet spot, where there's enough stars but few enough metals to yield significant gamma ray bursting. If you go further back in time, the rate drops off because the galaxy is less massive. It has physically accrued fewer stars at this point from the various merging events that make up its history. To see the full picture, let's now add the supernovae and gamma ray bursts together, which gives us a final threat map that looks like this. Notice how the sun's location in space and time puts us safely in a green zone, which of course makes sense given that we're here. Interestingly though, that wasn't always true. In fact, when the sun was being born 5 billion years ago, it was only then that our neck of the woods was starting to become hospitable. We can even take this map and convert it into a movie of galactic habitability over time, with again the red regions being dangerous and the green being friendly to life. Profoundly, we could very well be looking here at the story of life in our galaxy. Imagine the many civilizations that could have risen and fallen over the billions of years flashing before our eyes. So far we discussed supernovae and gamma ray bursts, but there are two other ingredients which are often stirred into the pot in order to make our galactic habitable zone. The first of these is planet formation, and the latter is planet retention. Now, planet formation has received far more attention in the literature, but remains, in my opinion, a debatable point. The argument basically states that there is a correlation between planet formation and stellar metallicity. More metals means more planets. Now, on top of this, the galaxy as a whole has a gradient in metallicity, such that the inner parts are more metal rich than the outskirts, and thus, on that basis, one might expect to find more rocky planets close to the galactic core. Some even take this a step further and argue that too much metallicity could be a problem because then you'd form too many giant planets that could actually inhibit rocky planet formation. So why am I skeptical? Well, the planet metallicity correlation is something that we have known about for a long time, ever since a seminal paper by Fisher and Valenti in 2005. They were able to show that there is an unambiguous correlation between giant planet occurrence and metallicity of the host stars. But back then, they didn't really know of any rocky planets, and so the authors were careful not to over-extrapolate their results. But 20 years later, we know of hundreds of rocky planets, and yet, despite that, we still don't have a clear answer. For example, in 2015, two teams looked at the same sample of 600 exoplanets, and one team, Wang and Fisher, concluded that there was a correlation, whereas the other team, Boucave and Latham, concluded there was none. Both of those papers have been criticized since, and in the years that have passed, despite many papers published on this topic, we still lack a clear consensus on this issue. So, whilst many galactic habitable zone models often invoke metallicity gradients and planet formation as a key attribute, I think it's a little bit premature to conclude that this is a significant and real effect. Now, we can be confident that Jupiter-sized planets do correlate with metallicity, but again, it's unclear whether the presence or absence of Jupiter-like planets has any bearing on the existence of temperate rocky Earths. Just look at TRAPPIST-1e for a counterexample. As you can tell, there's a lot we still don't know about exoplanets, and we should just be honest about that. There is one other effect though, remember, planet retention, and here I do have more confidence that the effect is real, although full disclosure, I am undoubtedly biased because this work was published by my own research team, the Cool Worlds Lab, led by Dr. Moya McTeer. The basic claim of our work is that the galactic bulge, that inner and busiest part of the galaxy, is probably too densely packed for Earth-like orbits to remain stable. Using dynamical simulations, we showed that 80% of bulge stars will experience a close passage of another star every billion years, where a close passage here is defined as 1,000 times the orbit of the Earth around the Sun. That sounds big, but it's actually close enough that the neighboring star could dynamically disturb the planetary system, potentially shuffling the planets around in their orbits, ejecting them all together, or even inhibiting planet formation in the first place. The precise consequences of these close passages is less well explored, but I think we can have good, confidence that close encounters of the stellar kind are a common occurrence within the galactic center. You know, it's remarkable to think that if our idea is right, then the galactic bulge should be teeming with free-floating planets, long-lost worlds drifting between the stars. So, putting this together, the idea that supernovae or planet formation is sculpting out a galactic haplozone is something I'm personally doubtful of. However, the idea that the galactic bulge is too dense for stable Earths and that gamma-ray bursts could be a substantial source of mass extinctions, they look more compelling. Even so, neither necessarily prohibit life. For all we know, a free-floating planet could still plausibly go on to form life in underwater volcanic vents, for example, and would be at an ocean depth sufficient to protect it from gamma-ray bursts. Now, whether these worlds will go on to harbor technologically advanced species is a different question. If technological civilizations always develop in a similar way to us, on similar planets to us, then sure, I grant you, this is an important issue. But if civilizations sometimes develop, say, underwater, or within the thicker atmospheres of other worlds, or even in anoxic conditions with more advanced DNA repair mechanisms, then gamma-ray bursts would not be as important as has often been assumed. Indeed, even without any of that, who's to say that a mass extinction event every, say, 50 million years is too much? With our one evolutionary timeline to reflect upon, it's highly speculative to assert that different rates of mass extinction rates are somehow prohibitive to the evolution of intelligent life. For all we know, higher rates might even accelerate their development. So let's just tread carefully here, for if evolution has taught us anything, is that we should not underestimate the hardness and adaptability of life. I think the idea of a galactic haplozone is attractive because it makes for a nice story. It explains why we live where we live in the Milky Way. But perhaps we don't really need an explanation for that. After all, there's nothing inherently unusual about our location to begin with. It already satisfies the mediocrity principle of being a fairly humdrum part of the cosmos, as Sagan would say. Now, had we instead found ourselves orbiting outside of the galaxy altogether, then I agree, that would be strange and perhaps would demand some kind of explanation. But for now, I can live with the idea that we live in a fairly ordinary part of the galaxy. In fact, I kind of like that notion. So let's remain open to these ideas, but at the same time, demand firmer evidence before we buy into these stories. And as always, stay thoughtful and stay curious. Thank you so much for watching, everyone. And before you go, I just want to give a quick shout out to say thank you to our latest donors. That is Brandon Pearson, Scott Thayer, and Trevor Edris. Thank you so much for your support, guys. If you too want to help us out, you can use the link up above and become a donor to my research team, the Cool Worlds Lab at Columbia. See you around the galaxy, everyone.